Now that we've seen all the Sn2, E2, and Sn1 mechanisms, I want to compare them together based on the steric hindrance that we have in a substrate. So in the first one, over here, we have our secondary carbon on where our leaving group is, next to a tertiary carbon over here, 3 groups. In our second example, it's the same thing. And in our third example, we have a secondary carbon next to 2 tertiary carbons. And so we're going to compare all 3 of these first 3 and see which mechanism will undergo. Now in the first one, since it's a strong base / strong nucleophile, NaOH, sodium hydroxide, and we have a tertiary neighbor, the E2 mechanism is going to be favored more than the Sn2 simply because of that little bit of steric hindrance. And so our final product will be the preferred elimination reaction. Now over here we have CH3SH with a strong nucleophile but weak base. Now this tertiary neighbor is, although it provides steric hindrance and slows down Sn2, it doesn't completely stop it, and so our product is going to be an Sn2 mechanism. So we have our methyl still going up with our wedge, and we have our CH3SH going down. And the H, the proton, the hydrogen, has left because it became acidic, and the sulfur, since it had a positive charge, would get rid of that hydrogen. Now, in this third example, we have 2 tertiary neighbors. Now, is this enough to make this an Sn1 mechanism? Yes. If we have 2 tertiary neighbors on the cyclohexane, that will make this an Sn1 mechanism. And so we will have a carbocation right here with our 2 methyl groups pointing upwards, and we'll probably get a hydride shift from one of them to make this a more stable carbocation from secondary to tertiary. And so we will get this intermediate right here where we have our methyl group, our carbocation, our other methyl group is still pointing upwards, and then CH3SH will finally attack at the very end, and we'll get our product. That is this. We have our methyl pointing up, and then we have our methyl group, our CH3SH. And I'm not showing stereochemistry here because there's multiple stereoisomers. Now in this last one, we have cyclohexane, and we have a strong base, strong nucleophile. Now bromine could, if it were to undergo E2, it would have to be diaxial. And so let's check if that's even possible. So here you have your conformation for your cyclohexane. If bromine is pointing down and it's axial, it should look like this. The methyl group that's 2 down from it is also pointing down, so it would be axial. And then the tert-butyl group, which is next to it, is pointing up, so it would actually be axial. Now a tert-butyl axial group is extremely unstable, and so this is not possible, which means that actually we have the other conformation that is the only conformation that we can possibly have, where bromine is pointing down. Over here, the other methyl group is pointing down as equatorial, and the final tert-butyl group is pointing upwards and it's equatorial. And so this is the only possible conformation. Since the bromine cannot go through the axial position, that must mean that we're going to have an Sn2 mechanism where our hydroxide is going to come in from the backside and attack, and our final product is an Sn2 product. So we're going to draw our cyclohexane over here. Our methyl group is still going to be going down. Our tert-butyl group is still going up. And then our bromine, our OH group, our hydroxide, is going to come in from the backside, so it's going to be going up. And so those are our 4 products for these situations where we're looking at our neighbors and see how they affect which mechanism we go through.